You should have received your tests back. If you did not, let me know and I'll make sure I resend those to you. Just like before, please do corrections on these and send them back to me. We'll get those points in the book for you. Today is our last lecture, our only lecture on statistics. So I will squeeze as much as I can into 2 hours. I'll warn you, I could go on for, well, I teach a full class in statistics and I could probably go on longer than that. So I will try to hold myself back and only squeeze what we have to know into here. But for those of you that are going to go on to a 4-year degree at some point, statistics is a required class in pretty much every 4-year medical related degree that I've seen. So it's something that you will need to know. Next week will be the test on statistics. And like I said, because it is our absolute last day of class and corrections probably won't be feasible for most of you, I will grade them and return them as fast as I can. So that if you do want to do corrections, you can. But I do try to be really nice on this last test and write it so that, I mean, the average score last semester, I believe, was like a 96 on this final test. So, I mean, I try to write it so it's a little bit simpler for you. Okay, so let's get into statistics. We talked a little bit at the end of the last unit about data graphs and types of data. And that's a big part of statistics. I put it in the graphing unit just because there's kind of that 20 minutes of extra time at the end of that unit that we need to fill, and the statistics units get short. But if we get a little time at the end of the day, we will come back and revisit that idea of frequency tables, of using that to organize data. But anyway, today we're going to focus on describing that data numerically instead of putting it into graphs. And to describe data numerically, we need to understand just what it is we're talking about when we say a distribution. What a distribution is if we take all the possible values. And we are talking about summarizing numerical data for the most part. We'll talk a little bit about categorical data here. But for the most part, when we're talking about calculating, it is numerical data. Let's talk about this last test. Let's say that last semester, this last test had scores that ranged from 85 up to 100. So we create a number line with values covering that whole range. And now let's say we look through the tests, and let's say actually I'm going to compile all the tests from the last several years so that I have enough points here. To get the feel of a distribution, you can't just have, a dozen points or whatever. You have to have several points so that you can get the feel of the shape of the distribution. Most of what we do in statistics requires that we have enough information. You can't just take a small amount of information. You have to have a large amount of information because things work out over time on average. They don't necessarily describe a single instance. So let's say I'm looking through my tests and there's a 91, there's a 96, a 92, an 87, a 93, another 91, a 98, a 92, it's an 86, 95, and I just keep filling in those points as I look at the scores. And over time, we see that those scores start to create a shape on this number line. And if I were to fill in enough of them, we would get a very distinguishable shape. So let's just say those are our points that we've graphed. If I kind of sketch in connecting the top point on each of those values or over each of those values, I get a shape something like that. You've probably heard the term bell curve before. And that's exactly what this is, the bell curve. The technical or mathematical term for it is something called the normal curve. In nature, for things that are randomly distributed, like scores on a well-created test, the height of people would be another example, weight is another example, all sorts of things out there, wages and salaries within a given field usually do this. This is the shape that the data would take if we created this distribution. So it's called the normal curve because that's the shape that data normally falls into. So if I look at this curve, now I'm going to redraw my number line down here so I've got a curve that's a little bit cleaner. So let's say I have that curve. One of the things I might use to describe it is something called the center. So I might find the center of this curve here and trace it down. That looks like about 92 would be the center of that curve. Now a normal curve, if the data is perfectly normal or close to perfectly normal, it should be symmetrical. So that center is literally in the center. I could take what's on one side and fold it over onto the other side, and it should match up. So if I take another bell curve or another normal curve, like this, it's the same shape because I traced over the top of it, but then I moved it over. So if I were to just try to describe the difference between these curves, oops, come on. I would say that this new curve, the green curve, has a different center. Its center appears to be at about 94. So the difference between those two curves is their center. They're exactly the same shape otherwise. Now I can draw a third curve that might look like this. This blue curve has the same center as my original purple curve. The difference there is that it is now narrower. The blue curve is only that wide where the purple curve was that wide. The term that's used for this most often is spread. Sometimes the term dispersion is used. How the data is dispersed or spread out around that center. So what we're going to look at is we're going to look at finding numerically ways to describe the center and the spread of these distributions. So let's talk about center. Now I'm going to start out with a set of numbers over here that we're going to use. So there's my set of numbers that I'm going to start out using. The first measure of center that we're going to talk about is something called the mean. Now the mean might not be a term that you've heard before, but the process is something you've done before. This is simply the average. The average that you learned how to do probably around 3rd or 4th grade, where you just add together the numbers and divide by how many are there. Now some terms I'm going to define here. N is the number of items in the set. So for this set here, we've got 1, 2, 3, 4, 5, 6, 7, 8. For that set, n equals 8. This symbol here means sum or add up. And X, or sometimes X with a little I by it, is each individual number. So the formula for the mean, depending on whether we're looking at the mean of a population or the mean of a sample, might use the symbol mu for mean of a population, or x with a little line over it called x bar for the mean of a sample. The mean is expressed like this. That's the sum of each of the values divided by how many are there. So let's add them up. I've got 7 plus 28 is 35, plus 13 is 48, plus 18 is 66, plus 15 is 81, plus 11 is 92, plus 16 is 108, plus 22 is 130. Please feel free to double check me on that because it is a Friday morning. We're going to divide by 8. So if I did my adding correctly here, 130 divided by 8 is going to be, what, 16.25? That looks like our mean. So that is the first measure of center. Second measure of center is something called the median. The median is the middle of the data. And by middle, I mean physically in the middle. To find the median, there's actually 2 steps. The first step is to put the numbers in order. So I'm going to do that here. I've got 7 is my smallest. Looks like 11, 13, 15, 7, 11, 13, 15, 16, 18, 22, and 28. Make sure I got all 8 of them there. I'm just going to number them. I'm numbering them for another reason too, because having them numbered is going to help me in the next step as well. So I've put them in order from smallest to largest. That's step 1. Step 2 is to find the position of the median. Now the position of the median is found by doing n times 1/2, or n times 0.5. If the median is in the middle, that means half of the numbers are on each side of it. For this data set, n equals 8, so that's going to be 8 times 1/2, which is 4. Now because n was even here, this came out to be a whole number. Because that's a whole number, the position of our median is between that location and the next. So it's between the 4th and the 5th number in the list. So we go up here, the 4th number is the 15, the 5th number is the 16. So to find the number that's between them, 15 plus 16 divided by 2. We average them together. Now when you do this on your calculator, and when you do the mean as well, I should have mentioned it up there. When you add them all up, make sure you hit equals first before you divide. Because if you do 15 plus 16 divided by 2 without hitting equals, it'll divide the 16 by 2, get 8, and it'll add it to the 15 to give you 23. That's definitely not the right answer. 16 plus 15 is 31. Divided by 2 should be 15.5 or 15.5. That would be the median of this set. And again, because n was even, it was between that position and the next position. So let me just do this. I'm going to add a number on the end of this list. I'm going to put 31 there. So now n is equal to 9 instead of 8. If n is odd, let's take 9 times 1/2. That gives me 4.5. Since this is a decimal, we round up. So getting 4.5, we round up to the 5th position. So the 5th number in the list is the median. So that's just the 16th. So you have those two possibilities. If n is even, as I said here, you're going to get a whole number, so it's between that position and the next one. If n is odd, you're going to get a decimal. You round it up, and that number is the position that the median is in. But again, for that to work, you have to have them put in order from smallest to largest first. If n is odd, it'll always be a decimal. Yes, because an odd number times 1/2 will always be a 0.5. Our third measure of center is something called the mode. The mode is the number that occurs the most often. Well, if you look in my set of numbers up here, no number appears more than once. So there would be no mode here. And for numerical data, it's really not useful. The mode really applies mostly for categorical data. Remember the difference between numerical data and categorical data. We talked about this briefly when we looked at the data graphs. In statistics, we're asking a question. That question could be, how tall are you? Or how much money do you make per hour? How long did it take you to complete this task? Whatever. That question is involving an answer that's a number. That's numerical data. The question could be, what's your favorite color? What wing do you work in? Or what specialty do you work in? Any yes or no question. Those are going to require your answer is going to put you into a category. Your favorite color, you might pick red or green or whatever. You might be working in OB or ER or whatever field your specialty is in. Those put you into a category, not a number. So that's categorical data. So for categorical data, you can't calculate a mean and a median because there's no numbers to work with. So we would use the mode. The mode is the one that occurs the most often. What is the color that's most often picked as the favorite color? What specialty has the most people working in it? That type of thing. So that's really where the mode is useful. When you learn about mean, median, and mode, usually in middle school, you'll have a little mini unit on statistics where you talk about them. They don't really make that distinction. But for numerical data, the mode is usually not horribly useful. Now, if we're looking at, actually, there's one more measure of center I want to mention, and then we'll look back at distributions and how these all relate. There's something called a mid-range. And a mid-range is back to numerical data, and it's just a really quick calculation. What the mid-range requires us to do is to take the largest number, called the max, add the smallest number, called the minimum, and divide by 2. So for our data here, the smallest number was 7, and I'm just going back to the original 8. The largest number was 28. So we would have 28 plus 7, which is 35, divided by 2 gives me a 17.5 for the mid-range. Again, that's a really quick number to find an approximate center. The problem with the mid-range is it's not what we call resistant. And resistance is a big thing in statistics. What resistance is, it measures how much it is affected by extreme numbers. We had that one large number on the top end of our data, the 28. That one large number affects our mid-range a lot. And we're going to come back and talk about how it affects the mean and the median here in just a minute. But let's look back now at our bell curve, that normal curve. If we have data that is normally distributed, I'm just going to use the word normal for that. The mode, the value that occurs the most often, should be the highest point on the curve. That should be dead center here. That's mode. The median, the value that's in the middle, should also be dead center. And if this data is perfectly normally distributed, the mean, which is that calculated average, will also be the dead center of the curve. So if this data is perfectly normal, the mean, median, and mode should be the same number. Now again, that only works out if we have a large set of data. If we only had 8 data points here, so most likely the mean, median, and mode are going to be different. In fact, we didn't have a mode for this set of data because no number was repeated more than once. If the data is skewed, and what skewed means is it's just lopsided one direction or another. This here would be what we would call skewed left. This here would be called skewed right. So skewed left, basically they're taking the left side and they're stretching it out. The left end of that curve and they're stretching it out. Skewed right, they're taking the right end of that curve and they're stretching it out. The mode is still the highest point on that curve. Now the median, because there's more points out there, is going to move slightly to the direction of the skew. The mean could change a lot. So as we were talking before, the mean is less resistant. The skew is caused by extreme values on that side of the graph. So here there's extreme values that are way smaller than the other numbers is what's causing it to be skewed to the left. And that mean is more affected by those really small numbers. If it's skewed to the right, those extreme values are on the right side. Now the right side would be the larger numbers, so that's saying there's numbers that are there's a number or two that are way bigger than the rest, causing that. And we get just the opposite effect. The mode is still the highest point. Median moves a little bit towards the skew. And the mean will generally move quite a bit towards the skew. So when we're asked, what do you view as the best measure of center? Now, I've already told you that the mid-range is not very good because it's overly sensitive. The mode, we said, really is only useful for categorical data. So when we're looking at numerical data, it's the mean versus the median. And if I were to ask groups without really showing them anything, just showing them what the mean and median are, most groups would say the mean is the more reliable, the better measure of center. And partly because it's just more satisfying. You got this formula, you're adding them up, and then you're dividing, and you feel like you're doing math. And it's that average that we've known since, third or fourth grade. But the example that demonstrates the usefulness of these, the one I like, and it's also another example that demonstrates how statistics can be abused, is 1983, University of Virginia. They advertised it in people that are graduating with a bachelor's degree in marketing that year had an average starting salary of just over $78,000 that year. Now, how many of you would drop out of school right now if I told you you could get $78,000 a year? I probably wouldn't be here tomorrow. I can be honest. That's an impressive starting salary. Now you go back to 1983, your average high school teacher in 1983 had a starting salary between $16,000 and $18,000. So $78,000 was a tremendous starting salary at that time. Well, what they neglected to disclose in that information was somebody who actually did graduate in their marketing program that year was someone by the name of Ralph Sampson. Now, I realize most of you were not born in 1983, so none of you are going to remember any of this. But Mr. Sampson, I barely remember it, just so you know, was 7'4". I was actually in about the third grade in 1983. Mr. Sampson was 7'4". He was the two-time NCAA Basketball Player of the Year and was drafted number 1 by the Houston Rockets, NBA team. Now, I'm guessing Mr. Sampson made a little bit more than $78,000 that year. He actually signed a multi-million-dollar contract. Now, you think about it, you got several $1 million on that one person. It takes a lot of $19,000 or $20,000 a year marketing graduates to average out a multi-million-dollar contract to $78,000. Mr. Sampson was the only one in that group to make more than $33,000 that year. In fact, the median, obviously this was a mean. They just said average. They didn't necessarily specify mean or median. When you hear that term, by the way, in practice of average, they can mean either one. I mean, we typically want to think mean, but they can mean either one. The median of that group was right around 24,000, which actually still wasn't a bad, average for a starting salary, but a little bit different than 78,000. So there you see how that one extreme value can really change the mean, but doesn't change the median so much. If this were a course where we had more time to get more in depth, we might even talk about something called outliers. And an outlier is a number that's just way out of line, usually way smaller or larger than the others. And you have to decide on those. Do you keep them in the data or do you take them out? Here, Mr. Sampson's salary was because he went to the NBA, had nothing to do with him having a marketing degree from the University of Virginia. In fact, he would have made that same amount of money even if he hadn't graduated. But there are times where those extreme values are based on that. In the medical field, the outliers are a huge deal. If you ever see any sort of a medical research document, the document itself, of course, could be hundreds of pages. But at the end of the document, there's anywhere from 20 to 100 more pages describing exceptions to the study. And what those are people that are excluded from the study because what happened to them wasn't related to what they were trying to study. For example, if we're looking at a treatment for a potentially fatal disease. And one of the people who's in the study receiving that experimental treatment dies in a car accident. Well, their death had nothing to do with the disease, and their death is not a valid measurement of how effective that treatment is. So you will take them out of the numerical calculations for that study, but you have to disclose somewhere that this person, usually don't name them by name, subject 1278 was excluded because, this circumstance. So you have to disclose those and explain those. But there are a lot of things done in those studies that the conclusion is made their death was not related to what we were trying to study. Okay, so the next step then is to talk about measures of spread. How spread out are these numbers? So we're going to look at another set of numbers here. The set of numbers we're going to look at, and I'm going to put them in order just to make life easier on us. Let's look at $10, $19, $20, $21, $30. So the first measure of spread we're going to talk about is the range. The range is related to the mid-range. It involves just the smallest and largest number. Instead of the maximum plus the minimum divided by 2, the range is just the maximum minus the minimum. So for this set of data, our range becomes 30 minus 10. So we get a range of 20. The problem with the range is it's not very discriminating. By discriminating, I mean it tells the difference between two similar sets of data. For example, this second set of numbers here, I would argue is more spread out. But if I calculated the range, the maximum is still 30, the minimum is still 10, it still has a range of 20. So the range is not good enough to discriminate between these two sets of data. So we need a better, more precise measure of spread. And what we use is called the standard deviation. Now the standard deviation is a 6-step process. And actually the result at each step has a special name. So we'll go through each step and what the name is. Step 1 in the process is to find the mean of the numbers. So looking at this set, the top set over here, I'm going to label it set A. We're going to do 10 plus 19 plus 20 plus 21 plus 30, which ends up being 100, divided by 5 is 20. So we get a mean of 20. Step 2, we're going to subtract the mean from each number. So I'm going to list my numbers here, 10, 19, 20, 21, and 30. And I'm now going to subtract my mean from each. So 10 minus 20 is a negative 10. 19 minus 20 is a negative 1. 20 minus 20 is 0. 21 minus 20 is 1. Perfect. And 30 minus 20 is 10. So I've subtracted the mean from each number. What I have there is called the deviations, or sometimes called the deviations from the mean. That's just how far each number in that list is away from the mean. If you wanted to double check your work at this point, if I were to add all those numbers up, the deviation should add to 0. Now, that should always equal 0, so it really doesn't tell us much at this point. So it's not part of our calculation. It's just one way to double check. Step 3 now is to square the deviations. So negative 10 squared. Now this is where you have to be careful. Remember, a negative number, when you square it, has to give us a positive result. On most of your calculators, to square a negative number, you have to put it in parentheses. So negative 10 squared should be a positive 100. Negative 1 squared is 1. 0 squared? 0. Positive 1 squared? 1. And finally, 10 squared is 100. These are what's referred to as the squared deviations, which makes sense. We just took the deviations and we squared them. Step 4 is to sum these up. Find the sum. We're going to add them up. So we add those. 100 plus 1 plus 0 plus 1 plus 100 is 202. This is referred to as the sum of the squared deviations. Step 5 is a little more complex. Step 5 is to divide by n minus 1. For this set of data, what does n equal?
Is that your mean?
No, n is the number of numbers in the list. So it'd be...
Oh, that's right, sorry.
Yep. So n is 5. So then n minus 1 is 5 minus 1, which is 4. So we're going to divide by 4, which gives us 50.5. That number right there is referred to as the variance. Now I said this was a 6-step process, so step 6 should be the end of it. You find the square root. So we take the square root of 50.5. $7.11. That is the standard deviation. Notice I only had like 5 numbers that I used for that. On a test, I would never, 6, 7 numbers would be the most I would ever ask you to do this for.
Thank you.
I've had professors myself that gave you like a list of 15 or 20 numbers and find the standard deviation by hand. And yeah, I really wanted to wait for them in the parking lot later. Okay, now, to prove that the standard deviation actually is a more discriminating measure of spread than the range. Remember, for these two sets of numbers, the range was the same. The range was 20. So I'm going to come back and use this second set. I'll label it set B here. And we're going to find its standard deviation quick. For 2 reasons. 1, to prove that it's different. And 2, just to give you one more chance to go through this with me before I turn you loose on your own on them. So our numbers here we're going to write down are 10, 11, 20, 29, and 30. That's our set. So you guys tell me, what's step 1?
Find the mean.
Find the mean. Seems like a long time ago. So 10 plus 11 plus 20 plus 29 plus 30 divided by 5. Well, we add those up, it adds up to 100. Divided by 5 should be 20. What's step 2?
Subtract the mean from each number.
Subtract the mean from each. And it's just kind of my preference to write them vertically like this. You might have a different way that works well for you. So I listed all my numbers out. I'm going to subtract 20 from each of them. What is 10 minus 20?
Negative 10.
Negative 10. 11 minus 20. Negative 9, yep. 20 minus 20? I'll give it, yep, 0, perfect. 29 minus 20?
9.
9. And 30 minus 20?
Negative 1.
Careful, 30 minus 20?
Oh, sorry, 1.
10, there you go.
Oh, jeez. Sorry.
It's okay, it's Friday, I totally understand. And of course, if we were naming names, those would be called the deviations. What's step 3? Square the deviations. Good, we're going to square them. So we have negative 10 squared is 100. Good. Negative 9 squared? 81. There you go. And 0 squared? 0. Good. Positive 9 squared? 81. And positive 10 squared? 100. And again, these numbers in this list should all be positive. If any of them are negative, you did something wrong. Any number squared should be a positive result. And of course, those are called the squared deviations. What's my next step? Add them up. Find the sum. If I add those all up, what do I get? 362, yep. 362, that is the sum of the squared deviations. What's step 5? N minus 1. Yeah. Divide by n minus 1. So what is n? N is still 5.
No.
Yep, the number that are in the list. You're exactly right. So n minus 1 is 4. So we are going to divide by 4. 90.5. You got it. What's the name of that?
Variance.
That is the variance. Good. In medical research, some of the tests they do will use the variance instead of the standard deviation. Partly because there are certain statistical tests that you can either square the standard deviation to do the test or you can just use the variance. Whenever you're given the variance, though, you should know you can find the standard deviation very quickly by doing what? Step 6 is the square root. And that's all it takes to go from the variance to the standard deviation. So So the square root of 90.5 is going to give us 9.51. Perfect. That is our standard deviation. So I won't ask more than 17 or 18 of those problems on the test next week.
That's kind of you.
I'd really only put one where you actually have to do the calculation. I got a feeling some of you would drive up from New Richmond to meet me in the parking lot if I put 17 of them on the test.
Maybe.
Okay, so it's a minute early, but let's go ahead and take our break. Let's come back at about 9:29 and we'll start up again.
All right.